All right. Sorry, it took me a while to set up. So, like I mentioned, on Monday, we'll finish up with our chapter. So, we'll go through the rest of our intermolecular forces, look at some math, but then I did drag half the lab to class so we could do some fun demos at the end today. I'll have to grab the liquid nitrogen, but all right, so let's start off. Unless there are questions or anything. Oh, is that correct? Oh, then you guys are absolutely correct. Sorry. Wow. Well, that's a great. That's good news. No. Uh, is it on the syllabus? Well, looks like I neglected to put it on the syllabus. But yeah, if it's Memorial Day, I was gonna try to pull up a school calendar really quickly. Trying to find. Yep, you're correct. I just wanted to double check on the official college calendar. Okay. Well, that's good to know. I don't know how I've totally forgot about that. But thank you for the reminder. So, no class. Oh, sorry. Like I said, with this new setup and then switching rooms, my poor computer is always confused. So, let me fix my Wacom really quickly. There we go. All right, so no class Monday. So if I remember correctly, and I was getting ahead of myself in lab today. So we still have, next week will be solutions. Not ideal, but we can cram it in on Wednesday. And so we probably won't have a quiz next week then in class officially. So we'll just use the 2 hours to lecture and do whatever else that needs to happen for solutions. And then next week is your last lab. And then week 10 is acids, bases, and then you'll have a little lab final. Yeah. So next Wednesday, you mean? Or the lab final? Okay. You and I should talk then and figure out either, well, I guess you could do the online lab practicum if that works. Yeah. Otherwise, I was just going to say you can make it up at some point. All right. Barreling towards the end here. So basically, 2 weeks of class, and then we have our final exam that last week. And then, of course, let me know if you need to take it early. I haven't heard anything from anybody in this class, but just let me know sooner rather than later. Yeah, so that's correct. So if you, and a few people in here already like jumped the gun and took the final, and so that's okay. I mean, you can do it in any order. But yeah, there's the online final, and however y'all want to do it. If you want to take both, if you want to take, one, like I'm perfectly open to any permutation combination. Yeah. So if you're doing it in person, we'll have the week 10 is when the lab final is scheduled, and it should be pretty like easy. Um, And so that would be the Wednesday during class. And then we'll do checkout as well for the in-person lab people. And then if you're taking the exam in person, I have the wrong date on here. I think this is like more online. But the final exam will take place on Wednesday in class. But if you're taking it online, then just try to get it done. Ideally by Thursday, but we can push it. And I might have dates slightly wrong. I think the 12th might be. I don't know if the 12th is actually the Friday. Does that sound like a good plan? All right, we might have to shut the door. Thanks. All right, so let's continue with our lecture. So we had left off with our van der Waals forces, right? So we had said that our van der Waals are with our nonpolar molecules or with anything, right? So all molecules and atoms have these London dispersion or van der Waals forces. And so now we're looking at the next type and the next one in strength. So our dipole-dipole interactions. And so these are interactions between polar molecules, so caused by that permanent dipole. So now thinking back, right, that's why we want to figure out is something polar or not. And then from there, okay, if something is polar, then it's going to have this dipole-dipole moment. And so now we're just looking at acetone. And I like the electrostatic potential map. This is also a good one. But basically we're saying that our oxygen carries our electron density. It has 2 lone pairs that we didn't draw out, but we could do that as well. You could also draw, to kind of help you see this, you could draw a resonance structure. It's not a very favorable one. So you could throw this double bond onto oxygen. But that again kind of hints at what's going on. So our carbon is more what we would call electrophilic. Our oxygen is nucleophilic in that it wants something positive. And so again, there's where we get our kind of partial positive, partial negative. And then they would be attracted to one another. And so this through space interaction is our dipole-dipole moment. So that interaction again between molecules. And so this permanent dipole adds to the attractive forces. The greater the dipole moment, that also influences the attractiveness, which we'll look at. But this is a good example, just comparing the London dispersion versus the dipole-dipole. So looking at ethane versus formaldehyde. So they have very similar molar masses of about 30. So okay, that the mass difference doesn't explain their boiling point difference. And so looking at their difference in boiling point, so right, ethane is -88 versus -19 for formaldehyde. I mean, both of those are still pretty low, but they are pretty small. But we see this large difference is due to the dipole-dipole interactions, right? So now we have this permanent dipole from our CO bond versus ethane, which is completely non-polar there. And then I like this chart. I think we had kind of briefly spent some time when we were initially talking about polarity and how to look up the dipole moments. And so now this is giving you an idea of, okay, well, the more polar something is, so comparing, again, propane versus acetonitrile. So the key being they all have very similar molecular weights, right, around 44 or so roughly. But then we see the increase in boiling point from the increasing dipole moment. So that's just, again, those electrostatic forces holding those molecules together more tightly. So then it just takes more energy in the form of our temperature here, right? So higher temperature, more energy to start breaking apart, again, those intermolecular interactions. And then hydrogen bonding, I call it kind of a more specialized dipole-dipole interaction. And so this is in a special case when we have an extremely electronegative atom and it's bonded to hydrogen. And so it's only in the case of oxygen, nitrogen, or fluorine that this occurs. So you might want to like highlight those, right? So they're the top upper right of your periodic table. So very electronegative. And so we find when hydrogen is bound to these atoms, it's hydrogen becomes what we call de-shielded, or basically we have almost an exposed proton. And so we can kind of think about that in this model here. So again, hydrogen's bonded to fluorine. And fluorine is so electronegative, right, that it's taking all the electron density. So it's pulling all that electron density towards it. We see that in this electrostatic potential map. And then again, that's leaving us with naked hydrogen essentially. And so we have the partial positive, partial negative symbols again to represent this. So hydrogen's again going to be partial positive. Our fluorine, or again nitrogen or oxygen, is partial negative. And then we can see this hydrogen bonding. And so now we can compare water and ethanol as well. And so why does water have a higher boiling point than ethanol? So not just the polarity, think of like how many. So how many hydrogen bonds does water have here? Yeah, 2. So this has 2 versus ethanol just having 1. So right here's our hydrogen bonding interaction from ethanol. And so that does give water the slightly higher boiling point. So water is again 100 degrees Celsius and ethanol is about 78 degrees Celsius. So really showing the power of the hydrogen bond, which is pretty fascinating. And then this starts to also get into things, we haven't quite stated it, but now's a good time to say it. You've probably heard of this, right? Like dissolves like. And so we can take it back. I think we already discussed this, but it's good to kind of revisit it. So remember we said, right, we have our water, and then our oxygen we said was partial negative. These hydrogens are partial positive, and so that's why they dissolve ionic compounds. So your cation is around your oxygen, your anion is around your hydrogen, versus something like nonpolar. So we could take like a hydrocarbon and then mix that with like fatty oil, which now I'm terrible at drawing fatty oils, but oils for the most part tend to be nonpolar. Uh-oh. Sorry, I was trying to pull up like oleic acid. So this is the primary component of like olive oil or other oils. And so right now we're just appreciating a long hydrocarbon chain. So if you spilled a bunch of oil on the ground or something, you would want a non-polar solvent, although that could get tricky for safety reasons. So you don't want to use hexanes. Hexanes are toxic. They get metabolized into a toxic byproduct, which won't hurt you in the short term, but long-term exposure is not great. But that's where you have pentane is a better choice, or heptane, so the 5 or the 7 carbon. I think toluene is okay, toxicity wise, but it does have a higher boiling point. It's not the most ideal solvent. And then I don't think we talk about this in this class, but now's a good time to kind of mention soap. So this is kind of the rough structure of soap. And so how you make soap is you take some sort of oil, right? You could take olive oil or another fat. They used to use lard. I mean, you can still use lard. And then you add sodium hydroxide or potassium hydroxide, or historically they use soda ash, which is, again, just another base. And then it makes this sort of thing. And so, again, like dissolves like. So you have this huge nonpolar chain on here to help dissolve all the fats, but then this part over here that's charged, right, that you made, basically this is the esterification reaction, it's called, or saponification, excuse me, saponification reaction, or the soap making reaction. And so it makes this little charged species, which then dissolves in water, and so that's how your soap is able to wash away your grease in the water. So it kind of solubilizes both nonpolar and polar. And so that's how we get, right, this kind of emulsifying action. And this is what I was looking for, this little micelle. And so they say that like the soap little forms these little micelles where the inside has all your grease ball that's solubilized again by this chain, and then the outside is hydrophilic and is attracted to water, so then again washes away, right, and keeps this whole little fat bubble solubilized.
That the same action in like emulsifications, like with polymers?
Yeah, yeah, so same sort of thing. Like usually like an emulsion is like a horrible intractable mixture of like two things, and usually we refer to it as like a water organic mixture, and then you can either, add something to separate that emulsion, or yeah, like polymers are going to be adding two things together roughly. I'm not like the biggest polymer chemist, but and so again, those hydrogen bonding forces are going to be the strongest now, since we have a really polar interaction, so they're stronger than the dipole-dipole or the London dispersion. And so substances that can form hydrogen bonds tend to have higher boiling points and melting points. So we've kind of seen that with water. Again, water is so tiny, but has a high boiling point. And then again, just re-emphasizing that we're not breaking any covalent bonds. So even though it's really strong, these hydrogen bonds, they're only about 5% the strength of a covalent bond. So we're not, again, breaking bonds in this. And again, just another comparison. So ethanol, we can name the bonding forces. So it's going to have hydrogen bonding. And it would still have, right, dipole-dipole and dispersion forces. Versus, which ones does dimethyl ether have? So it has that oxygen, right? So what do we usually assume if there's an oxygen in the middle? So it's bent, so then that's kind of telling us that it's like polar. Yeah. So then, It goes back to like the fundamental Lewis dot structure, right? So if you have an oxygen in the center, you know it has those two lone pairs. So then it can only have two things kind of coming off of that. So that kind of helps visualize it. But then also with oxygen, right, it's electronegative to begin with. So that's also going to hint to like polarity. And so this probably isn't like the most polar thing, right? We could go back. Where's that other chart? So here's dimethyl ether, right? So it is 1.3, so still polar, but right, it's not acetonitrile of almost 4. So everything in context and relative. But yeah, so then this has dipole-dipole and still would have dispersion. But again, we're appreciating this huge difference of negative 22 versus 78, all due to that hydrogen bonding. And then we often see this chart, or you may be shown this chart on your exam and asked to comment about it. And so all it is we're looking at our molar mass trends for the most part, so especially group 4. So increasing molar mass, increasing boiling point. But then we want to point out our anomaly of water. This graph doesn't have ammonia or HF on there, but other graphs sometimes show those substances. And so again, we're just pointing out the hydrogen bonding phenomenon. Okay, so now let's look at surface tension. And so usually I play a video of the lizard. There's this lizard that walks on water, but I think I'll skip that today because I brought a demo for surface tension as well. Oh, nice. Where were you? Oh, nice. Yeah, that's usually the video of like Jesus Christ lizard. That's funny. Is it in Spanish then? I can't think of what lizard is in Spanish right now. All right, so let's look at our surface tension. And let me pop out. Give me 1 second. Trying to do. Okay, I think that works. Except my video is kind of crooked. Try to put that somewhat upright. Yeah, let's okay, this isn't hot, my hot plate. I'm just trying to get a better camera surface here so we can see. I always joke, I need a producer. All right, so now let's look at surface tension, and we'll do the demo that, I mean, you may have done it in class in high school, but it's good to see it again. And so surface tension is our property that results from our tendency of liquids to minimize their surface area, but it's also like how attracted they are to each other. And so we can see the relationship. So looking at water, so again, water is polar with our hydrogen bonding, and so it has a pretty high surface tension. And then we remember, okay, well, water kind of beads up, and so that's what I want to show with our demo. Versus something, so I didn't want to drag out, so this is a formula for benzene, C6H6. I didn't want to drag out benzene because benzene's carcinogenic. I actually don't even think we have benzene on hand, but I brought something similar out. So instead of benzene, I brought out cyclohexane, which is still nonpolar. I'm going to draw it like this, but I'm going to show you a picture of it because this is one of those ones where 3D does matter. So it's not flat. Cyclohexane is not flat. Benzene is flat. Cyclohexane has this 3D structure, which is more appreciated by this kind of drawing or probably this kind of 3D representation. All right, but again, all we need to know is it's nonpolar. And so have you seen this demo where it's like, how many drops can you fit on a penny type of thing? Yeah, so you've probably done this in class. And then I don't know if when you've done it, you've compared it to an organic compound. And so I'll kind of do what I call a rush demo of this. And so this is water on the front, and so you can put a lot of drops on there and get it to beat up pretty nicely. We can try to keep going. I didn't keep count, but but at least in the camera you can tell how it's beating up nicely. And then right away, I don't know if you can tell that the cyclohexane is flatter. It's kind of going. Oh, I'm getting a lot of beads on that cyclohexane. Oh, and there it goes. See how the cyclohexane kind of spilled over a little more readily. And then maybe we can push the water some more. Yeah. And if we were in lab or taking more time with this, we'd be counting them and having a competition. So you can see my water bubbles still growing. But all that, oop, see, I finally busted it, is due to surface tension. So again, key takeaway, right? Stronger our intermolecular forces, the stronger our surface tension, and so then that causes it to beat up, again, compared to an organic that does not have as strong of intermolecular forces. And so like we saw, okay, stronger the intermolecular attractive forces, the higher the surface tension. And then if we were to raise the temperature of the liquid, this would reduce the surface tension. We're not really going to do anything else with that statement. That's just kind of so you understand that. And again, you want to think about the molecular level, what that means, raising the temperature so the molecules are moving faster, but then that's going to disrupt, right, those intermolecular forces more. And so again, that will weaken the surface tension. And then, like we saw, this is why things can float or walk on water, like we discussed, even though technically a paperclip or the lizard, right, would be more dense than water, but it gets enough cohesion and keeps moving quickly enough that it can float there. And then vapor pressure is also related, which again kind of makes sense. So the weaker the attractive forces, then the more molecules will be in the vapor, right? So they're not stuck, they're floating around. And I mean, I'm always thinking of real life examples with this. I mean, I'm not the biggest drinker, but part of why I don't like drinking is, right, you open up the bottle of wine or something and then you're hit with that alcohol, ethanol smell. And so part of that is from the lower vapor pressure of that. So that's why it feels like you're hit with it. So I'll just kind of put ethanol smell. Or other experiences that I've had, like if you ever open a huge 20-liter drum of ether, so diethyl ether in the summer, that's gonna, kind of hit you in the face with the ether from that high vapor pressure. And again, that kind of goes back to the boiling points. And so the weaker the attractive forces, the higher the vapor pressure, and again, right, the lower the boiling point. So all that's related. And then just like we've been seeing, okay, higher, uh, and then yeah, the higher the vapor pressure, then that just means the more volatile or the more quickly it evaporates. And so this is what I mean. This is a graph that's shown a lot. And so this is just emphasizing the previous point that we have our vapor pressure, so something with a lower boiling point and weaker intermolecular forces like diethyl ether. So it's going to have a higher vapor pressure. And then when it crosses this threshold, so does anybody recognize what 760 torr is? Excellent. So 1 ATM, and then this corresponds to normal boiling point. So that's why that's labeled. So right at our atmospheric pressure, this is when it's going to boil. And again, that means that their vapor pressure is 760, so equal to the atmosphere. And so you can at least appreciate the curves. So ethanol, right, obviously higher than diethyl ether since it has 1 hydrogen bonding. And then water with 2. And then again, we can appreciate as we increase the temperature, right, that really changes the vapor pressure. All right, this is like our last bit from this chapter. It's a bit lengthy though, because now this is all the math part. But you'll at least be rewarded with some fun stuff, hopefully. All right, so we have our energetics of melting. And so now we have, when we have high energy molecules are lost from the solid, our average kinetic energy is lowered. So now we're kind of right describing how we solidify something. And so if energy is not drawn back into the solid, the temperature will decrease. And so melting is an endothermic process, and I think you've kind of played with that, versus freezing is exothermic. So again, just kind of thinking back to this week and the previous week, we melted wax, right? We saw we had to heat that up, and then you took it out and you froze it, right, and saw, again, the temperature decrease of that. And again, melting requires the input of energy. You also kind of played with that sodium acetate today. So you had to heat it up, right, get it solubilized. Again, talking about melting something. So getting those intermolecular forces to kind of start breaking up so that it moves right from the solid to the liquid state. And so there's kind of 2 main points to a heating curve. So first we have just changing the temperature of something. And so we have the Q just means heat. So how much heat is either lost or gained. And then this formula is all based off of the specific heat here. So CS is specific heat. And so that tells you, right, how much energy it takes to change 1 gram typically of the substance, 1 degree in change. And so that's where the mass and the temperature come into play. And then hopefully, I think you guys saw this. I was grading a lot of energy labs. And so then, right, the whole point of last week with our wax was that once our temperature reaches our melting point, all the heat goes into the solid, or vice versa, right? When we reach our freezing point, all the heat or leaving goes into solidifying, right? So it goes into our state change. And so anytime we see a plateau, again, like you saw with your wax, right, it kind of plateaued out. And so that plateau means we're doing a state change. And then the state change requires a different little variable, so we'll look at that, and then we'll piece the math together. And then, like you saw with your wax, right, once your plateau kind of finished, it finished solidifying out, then the temperature could continue dropping again. And so then the state change, so this is, all right, this is for our state change. So we have the heat of fusion. And so fusion is going to be for either melting or solidifying, or crystallizing would be the other term. And so it shows us here, right? So our however much heat it takes to melt something, the crystallization, how much we have to lose to crystallize, right, is the opposite of that. So opposite and equal. And so again, melting is endothermic, and then crystallization would be exothermic. And then we'll go through, like I said, we'll go through all of this. And then we also have the heat of vaporization. So vaporization is from either liquid to gas, so boiling, or if we're going back, right, gas to liquid, or condensation. As you might expect, our heat of vaporization is much larger than fusion, right? And just again, kind of think about how that makes sense. Vaporization, they're going to be in the gaseous state, so they should have more energy. And then if you were to ever come across a sublimation problem, so remember sublimation is solid to gas directly, or vice versa. But for sublimation, you would add your heat of fusion and your heat of vaporization, and that gives you your heat of sublimation. All right, so let's kind of walk through the math. So I might start, I want to start heating up water. So while we kind of walk through this math, I just realized I need some ice too. I wanted to do our can crushing demo and then some other just kind of fun things that we should do. So this will give our can time to warm up. All right, so that's gonna start heating while we walk through this math here. And so let's look at where we're going overall. And so we want to take 1 mole of ice from negative 25 degrees Celsius and take it all the way to 125 degrees Celsius in the gaseous state. So let's kind of walk through how we would do this. And so again, this is based off of our specific heat of ice. And then notice that ice is slightly lower than the specific heat of water. So it's 2.09 joules per gram of ice, right, times our change in temperature. And so we want to take it from wherever we're starting, right? So this would be given in the problem. And then we want to stop at the melting point. So I probably wouldn't make you guys do anything too difficult, but for my 200 level class, I give them all sorts of melting points and substances. But for us, we'll probably stick to water if we do some of these simple calculations. And then, okay, we have to do some conversions, right? So we're at a mole here, which is 18 grams. So just getting the molecular weight of water, and then we can figure out how much heat was added. So we do 18 times our specific heat here, times our change in temperature, so 25 degrees Celsius. And then it gives us the answer in joules, right? Again, based off of that specific heat. But then they've also converted it to kilojoules. That'll be useful later when we're adding them. So sorry, let me pull up my calculator. Just so we can verify that yes, the numbers on here are correct. And so let's plug it in ourselves. So 18 times 2.09 times 25. Okay, so that's how we get our 940.5 joules, which they've rounded to 3 sig figs. All right, so now we're... Oh, this is just a constant that you could like look up. So you could like, yeah, so you could search specific heat of water, but then it's at a solid, so in its ice form. But yeah, all these are standard thermodynamic values that I would provide on an exam. All right, so now we're at leg 2 here, and that's our state change. So we're melting. And so that's where we look up our heat of fusion. So again, this is another value that we look up or are provided. So standard thermo value. And again, if you wanted to do gold or whatever substance, right, you just have to look up the heat of fusion for that substance. And then this one's at least a little easier. Again, the formula is based off of this. So now it's kilojoules per mole. We have 1 mole. So that's how we get 6.02 kilojoules for that transformation. And then with these graphs, it could either be heat or sometimes time or reaction time on this x-axis. So we're just continuing to add heat. So now we're here. So I'll pause for a second. And then, okay, so now we're at leg 3. So that means we want to heat our water, right? So we want to take it from 0 degrees Celsius, but as a liquid, and then take it up again to our next state change. Now we have the specific heat of water now as a liquid. So there's this 4.18 joules per gram degrees Celsius, which is a number y'all might be familiar with. Again, basing it off of our formula. So I need grams again, so 18 times our specific heat of the liquid form of water times our change in temperature. So I'll just punch this one again so we can all see. And so that's in joules. So we get the same answer. They round to 3 sig figs, and it's about 7.52 kilojoules there. So now we're at 100, right? Now we're ready for our state change. And so last state change, well, now we need our vaporization. And again, right, base it off of your formula. Look at what you're given. So kilojoules per mole, so multiply times our mole amount, so 40.7 kilojoules. Again, appreciate how much energy that took. But you probably know that from watching your pasta water boil, right? It takes a long time watching that pot, so that's why it takes so long to get it to that boiling point, right? So much energy there. And so now we're at our vapor point, right? We've done our state change. We're at a gas. But now we're just saying how much energy would we need to add to that gas to get it to 125. Oh, also looking at the state change, that's why people say, right, there's the steam is more dangerous, so there's like more energy in the steam. I don't know if anybody still like steams their pores or anything, but that's why you should be careful.
So is that showing where it has that long bar that all of the molecules are at that same level until it reaches a point and then goes up? But they're not in different stages of transition?
That's what it's implying, but like kind of real world, right? It doesn't work out that
Yeah.
perfectly, but yeah, that's the idea is like basically all of it would make the state change and then you continue it, but yeah. I totally get like the real world does not work out as ideally,
Yeah.
but yeah, that's what that's implying is like all the energy just goes in the state change and they would all be again experiencing that heat being added evenly because I think that's where the real world and this like don't match, right? Maybe you heat something, you're only heating the bottom and then that kind of messes this up realistically. And then the last part, again, just going through the math, you would look up or be provided with our specific heat now of steam. Appreciate that it is less than liquid water. And then again, I'm just basing the formula off of our units. So 18 grams again times our specific heat times our change in temperature, so 25. And so let's plug this one in. And so we get 904 joules, but then 0.904 kilojoules. And then probably the last thing we wanted to do with this problem is we'll find, well, what was the total energy? And so that's where I said adding things up in kilojoules is useful. So now 0.904 plus 40.7 plus 7.52 plus 6.02, oops, plus 0.941. And so the total energy of this entire transformation of again going from negative 25 Celsius to 125 Celsius, so solid to gas, was about 56 kilojoules total. All right, I think, uh-oh, shit. I think that's about it for lecture. Sorry, I used a bad cable. I think that only affects me and not y'all. All right, this thing, oh, looks like it's steaming. Okay, I forgot ice, so I was gonna run and grab some ice. But then I have just a bunch of fun stuff to play with. I do have your quizzes too. I need to run and grab those. But I brought, well, I didn't bring, I have liquid nitrogen, so we can play with it as well in some other kind of demos. But let me run and grab some ice, and then we'll look at crushing this can. So going back to the mini demo. So give me 1 second, and I'll grab the quizzes too. I've been muted this whole time on stream. That was good. Okay, let's see if I can blow up a balloon. Okay. Obviously I can't. That's embarrassing. Okay. I'm ready to like fill it with oxygen gas just because I can't blow up a balloon. Nothing like blowing up a balloon under pressure. Why is this balloon so small? I feel like a maniac here. All right, well, I'll do a baby demo. Although now I won't be able to fish it out. Oh, but right, going back to our principles. So if we cool it down, it condenses pretty quickly and then just heats back up. Other fun things I have, these are like a little harder to show on camera, but this thing just has kind of a pressure volume relationship. So right now it's at 12, the pressure's at 1, and so then we could move it, and so it's kind of tedious, but we can half the volume. And so if I ever make it to 6, and so now we're at 6 roughly, and so that means, right, my pressure has doubled. So again, looking at our pressure volume relationship, I'm not actually sure what this does. I brought it along, but now I realize I don't know what to do with it, so I'll leave it there. All right, I think that's all the entertainment I have for today. So I'm trying to think if there's anything else I wanted to do with the nitrogen. I think that was it. But if you want to eat marshmallows, then now's your opportunity. Or just play with it, play with the liquid nitrogen. Obviously be careful with it. So yeah, let me know if you want to play with it. Otherwise, we have our quiz, or it's available online. Anything else so we should say? I'm trying to think if I did all the demos too. Yeah, I think that was everything. All right, I'll stop the lecture, or I'll hang out on stream just in case.